So why do you need CleanWave? It's very simple. CleanWave is an application that allows you to remove noise or drums from an audio recording. And there are a few applications where it can be used. So where do we provide, what value do we provide for the users? First of all, you can remove drums from an audio recording. Let's say you have a favorite song and you just want the melody part of it. We can do it. Same way we can remove the melody and leave the drums, so you can freestyle over the beat. Or let's say you had a podcast with Joe Rogan and you have annoying clicks in the recording. You can remove it easily with our application. Same thing for static. We can do it all and remove all noise from your recording. So let me demonstrate how the application works with an example. Over here, I have my website. It has an upload section. So let us choose a file. For example, this one. Over here, I have different settings. I'm not going to go into detail right now, but right now it's set up to extract the melody better than the drums. So let's click upload. And over here we see our original file. This is the waveform, and this is the spectrogram. On the spectrogram, the horizontal lines are the melody and the vertical lines are the drums. Let's hear the recording. So as you can hear, every time the drums hit, it makes a vertical line on the spectrogram. So we already received the response from the server. Here we have a harmonic component. This is just the melody. And on the spectrogram, there are no more vertical lines, so it means it worked pretty well. And we also generated a percussive component, which is basically drums. It has some artifacts. I changed some settings. I increased vertical median filtering and decreased the horizontal median filtering, which should have an effect on how prevalent the drums are. So let us see. Let's hear it this time. Much clearer. So in order to really understand how the application works, I had to learn a lot about theory of sound, and I think it's important to understand how this magic happens and what's the fundamental thing happening in the microphone. Essentially, there's just a membrane that gets pushed by the air gets pushed by the source of the sound, and as you can see here, it kind of pushes the membrane inwards, and that registers the positive values, and they're represented as peaks on this sine wave. And once they bounce back by inertia, this membrane gets pushed backwards, and that registers negative values, and that's what creates this kind of sine wave-like diagram. And then we record these values. We perform some frequency analysis on it by using Fourier transform, which is a formula that helps you break down a complex wave into a bunch of smaller, simpler waves, and then analyze how much of each wave is present in the recording. This picture is showing that really well. You have time domain, which is like your regular audio recording. You break it into smaller, more simple, more easy to describe waves, and you make this kind of chart in the frequency domain to represent how much of each frequency is present, how strong is each frequency. And then to give you a better report, you slice that signal into smaller chunks, and you apply that formula to each smaller chunk. Instead of like the whole thing like we had here, you have the whole recording, apply Fourier transform. That's not very accurate. We need data about specific points in the recording, so that's where the window function applies, and that's how you get short time Fourier transform, which you can then represent on the spectrogram. Spectrogram is a special way to represent sound because each rectangle is a smaller part of the entire signal, and each horizontal line here vertically represents how much of each frequency is present in that rectangle. So how do we know what sound to remove? To simplify it, the membrane wobbling speed, I know it's crazy term, but I think it's very descriptive. So the wobbling speed over 1 second defines the pitch of the recorded sound. If it did 2 cycles of bend outwards but bend inwards, it is considered to be 2 hertz. And also, depending on how far it bends inwards, that's the amplitude, that's the strength of that wave, or the volume of the signal. It turns out that on the spectrogram, the vertical lines represent percussion components, which is your drums, and horizontal lines, they show you more the melody. And again, this spectrogram, each rectangle here is a part of your audio recording, and each individual line here shows you how much of each frequency is present in that specific small part. Now I would like to showcase my code for the front-end part of the application. I used React as my main framework for this project, and I also used wavesurfer.js for visualization of sound, for spectrograms, for playback, all things that have to do anything with the audio. I used surfer.js. So let's look at the main component, app.js. That's our parent component, the first thing that gets loaded. Over here we have, I mostly used useState hook to control the state of different components of the app. If we scroll down below, we can see our fetch requests to the server, and we see our other components here being instantiated in the app.js. So let us look at the first component. That should be waveform. Waveform is just like a sine wave that represents your audio signal. And if I open it here, it's pretty simple. Over here we have a spectrogram. We use the useEffect hook to make sure that when the state changes, we reload the whole plugin. Inside the useEffect hook, we create an instance of waveserver, load the data into that chart, and we return the markup, which is pretty straightforward. And finally, one of the most, if not the most important component, is the file upload. As we can see, we have a few states here for different options that we set before sending the file. Additionally, we have all of this helper functions, and most importantly, we have a fetch request that sends the file through HTTP request to the server and awaits a response. And once we get the response, we update the state on the app.js file. We have like a parent state, and that parent state then tells the spectrogram and waveform components to go and request for the files on the server that are relevant to this component. So our React application can be summed up using this flowchart. We have the main component, app.js, which is the parent component, and file upload component makes an HTTP request with the file, sends it over to the server, expects a response. Once it gets a response, if it's a positive response, successful message, it tells the app component to tell other components, in this case waveform and spectrogram, to go to this to go and make a request to the server for the relevant data that they need to load the player on the page. And here's a more detailed breakdown of how these components work. In short, file upload component allows the user to select the audio file, input filtering parameters and send it to the server once the successful message has been received. The waveform component gets the audio file and populates the player. Same thing happens with the spectrogram. Now the backend part is structured more like a queue. In order to handle multiple requests at the same time, we only allow up to five processes to run at the same time. All other processes get placed in a queue or stack, and they wait until there is a slot available to run this process with other four processes concurrently. So to go a little bit more into detail, we have different API endpoints. In this case, upload, load track, get harmonic, get percussive, and see uploads. Realistically, we only use upload and get harmonic and get percussive right now. The other two we decided to remove for now. And here's a more generalized flow. User uploads the file, the task gets added to queue, it gets processed with a Python script, and generates two files, one only with melody, the other one is only with the drums, and saves it on the server. And then React front-end application requests this file. And a more high-level overview, we have the client application, which is our React application. Make a request for the upload route. It adds this task to the queue. The file gets processed, generates two new files, one only harmonic, one only percussive, sends a response back to the client, and the client makes two new responses, one for the harmonic file and the other one is for the percussive file. To better demonstrate how the Python program works, I created this diagram. In short, what it essentially does is it computes short-time Fourier transform with the parameters that we pass to it through the command line input, and essentially it applies a mask. A mask is like an array with a bunch of ones and zeros, and if you multiply your original array by that, I should better say matrix, by that other matrix, whatever is zero gets removed from the original array, and you clean up your audio file like that. And then you just reconstruct your audio file with these changes, having removed this unnecessary sound waves that you don't want to hear in your melody. The actual code in my backend application is structured the following way. I have a few folders. I have utilities, uploads folder, routes, output folder, node modules, something generated by Node.js. And I have my main application, my harmonic percussive separation utility, and where it starts actually is with app.js, but I tried to follow Professor Chuang's advice and make it more modular, more up to modern standards, so I just decided to break it into routes. So depending on what is requested, my application directs this request to the right utility, you could say, and our queue manager puts a certain request in a queue, and once when it comes to the end of the line, we run the process file.js, which essentially just instantiates our Python program. It's a lot of code, but it's not really doing a lot here. And then our hpss.py runs, and this is the main program. I have HPS function with a lot of different parameters. One of them is the original array, hop size, window length, amount of filter on the horizontal part, amount of filter on the vertical part, and other different options. But over here we compute our short-time Fourier transform. Then we set up a lot of things for the next step. We create a binary mask, and we multiply our original input signal. Actually, that's already a Fourier transform version of our signal. And over here, we remove the frequencies that we don't want to see. And finally, we put it back together, this modified file. And at the end, we just store it in our outputs folder, two versions of the same file, XH and XP. And these two files get sent back to the server, back to the client. I'm hosting my application on Vercel, my front-end application, and I have some sort of CI/CD pipeline set up in a way that when I push something to my GitHub repository, it gets automatically updated on my domain, on my website. And I have a similar system set up on the backend. I use render.com. It's a free service, very easy to use. It takes some time to set it up, but after that it's pretty easy to use it. And it is limited though, but I think it's good for free. And also when I push something to GitHub repository, it gets updated on the backend automatically. And finally, I wanted to run a few other demonstrations. Here I have the following input file. Sounds this way. I have generated a harmonic component. As you can see, there are no drums in this recording and the percussive component. I tried again with different settings for the percussive component. Over here I changed some values, and here's what I got. So I'm not sure why it removed the bottom parts, which is unexpected. I'm not sure why that happened, but the point is you could play around with the settings and achieve different results depending on what your goals are. And here's another interesting experiment. It also is interesting to see, depending on how you change the values in the options, you get all sorts of different effects. So this time I tried to make a larger window size and larger hop size, as well as apply more horizontal median filtering. And this is the original file, some nice Spanish guitar. And the harmonic part didn't turn out so well, but there is an interesting effect to it. So it did separate the melody, but it doesn't sound right because guitar consists of kind of, when you pluck the string, it also makes a percussive sound. And let's listen to the percussive part. So it sounds like it did a way better job on the percussive part, although you still can hear some melody there, but this is how it plays out sometimes. This is the end of my presentation. Thank you for watching and listening. I really enjoyed this semester, and I really feel like I learned a lot during that time. Thank you, and I hope to hear back from you soon with a review, or maybe if there's anything I should be updating, please let me know. Thank you again. Bye-bye.